Hi everyone. Now I would like to present my final year project, which is the design and development of high accuracy shuttlecock launching system. So first of all, I want to introduce to you what is shuttlecock launching system. So it is an electromechanical machine which projects shuttlecock to the players mainly for training purpose. So the figure 1 shows one of the product available in the market, and the SLS machine basically contain two parts. First is the feeding mechanism and second is the launching mechanism. Why do we need shuttlecock launching system? First is to assist coaches in conducting training courses. So the coaches can focus mainly on coaching and not playing while in one-on-one training session. Second is to benefit players, which makes the training session more focused. The machine settings are duplicated accurately in any shots, unlike human opponents. So the machines can be set to launch the shuttlecock to a specific area or towards the players, so that they can train a specific skills. Next, this is the system overview of the machine. So it consists of controller, actuator, and sensor feedback. First of all, the data input can be the desired position S and Y to launch the shuttlecock to a specific location. Then the controller consists of the trajectory equation. Then goes to the process and produce the output. Next is the problem statement. In this project, the launching accuracy is one of the important factors to the shuttlecock launching system, either in feeding or launching mechanism. However, to make this reliable, one of the methods is to understand the trajectory of shuttlecock motion. So the basic shuttlecock trajectory consists of these three types. First is the smash, neck shot, and neck lift. However, in my project, the scope is in the neck lift trajectory. So the objective of this project is to develop a shuttlecock launching system that follows the existing trajectory equation with lateral swing design. Second is to test the accuracy of the shuttlecock launching system and improve the performance. So there are basically three types of shuttlecock launcher available in the market. First is the Apollo trainer, second is the Night trainer, and third is the Siboasi machine. However, these three shuttlecock launcher are too expensive to the consumer. So these are the two types of common launching mechanism used in the current products: the double high-speed rotation wheel and the impact mechanism. So in figure 4, showing that the two wheels are attached in the machine to draw the shuttlecocks, while in the impact mechanism, the racket is mounted on the machine and contact with the shuttlecock during the operation. So this is the the flow chart of the methodology. So I will examine the existing trajectory equation, then design the product, the prototype, and then program by using the Arduino. Then compare the accuracy. If it is achieved 90%, you finalize the report. So for the development of prototype, how do we calculate the feeder rate? So in this figure, it shows the diameter and number of teeth of gear design. By using these two formula, we can get the speed it will produce by this design. So by assuming the number of teeth given the diameter, can readjust the value and get the desired speed. And therefore the ratio for gear 1 and 2 of the diameter will be 3680 and the number of teeth will be 45 and 100, which is in millimeters. So next, how do we design the feeder cam? In this figure, it shows the space constraint of cam design. First of all, the two cams will basically rotate 360 degrees, and then in the standby mode, it can grip the cord of the shuttlecock and pull down from the storage. However, due to the back end of the cam, the shuttlecock will be affected. I mean, the motion of the shuttlecock free fall will be affected, and thus the distance D will be designed to 80 millimeters apart, which is greater than the diameter of shuttlecock of about 70 millimeters. So next, how do we select the motors in feeder mechanism? So in feeder mechanism, the main parameters is the speed, which is the main factors to be considered. So the feeder mechanism should load 2 shuttlecocks per second. So by using this formula, the number of revolution per second can be found, and the torque required can be calculated. So from the specifications of the chosen DC gear motors, the speed and torque which we calculated is said to be achieved by this type of motors, and thus the SPG 3020K is chosen. Next, how do we select motors in launching mechanism? So in the launching mechanism, both the speed and torque are important. These two, the speed of 2600 RPM is being proved by one of the journal to launch the shuttlecock to the back line of the badminton court, which is the longest distance. And by using this torque formula with the MR, which is the mass of racket, MS mass of shuttlecock, T is the time, R is the length of the racket, and V is the velocity. So to find the velocity, we'll use the trajectory equations by input the S and Y axis to get the VO for X and VO for Y. Yeah, so substitute the S and Y to the trajectory equations. We can get VOX, VOY by using the trajectory trigonometry function. We can get the desired velocity, and thus the torque required can be calculated as 0.39 Newton meter. So from the specification, the data sheet of this scooter motor, we can see that with the torque of 0.39 Newton meter, which is calculated, we can get the speed of the motor about 3000 RPM. That is sufficient to drive the shuttlecock, and thus the 350 watts of electric scooter motor is chosen. Next, how do we develop an ideal height for SLS prototype? Due to the structure of shuttlecock, aerodynamic force exerted on it will lead to the deviation of shuttlecock free fall. So these 4 figures showing the angles deviation at different heights in millimeters, which is for 500, 600, 700, and 800 millimeters. So you can see that as the height increases, the angle deviation of the shuttlecock will be decreased, and this is we can describe the relationship as the height is inversely proportional to the angle deviation of the shuttlecock, and thus we will need to get the least angle of deviation. We will use the 800 millimeters of height to develop the prototype. Next, how do we analyze the performance of shuttlecock motion trajectory? First, the project has to consider the reliability of the system. A model-free trajectory simulation will be executed in MATLAB to assure the A model-free trajectory simulation will be executed in MATLAB to ensure the parameters are reliable. Second, the project has to consider the accuracy of the shot. So there are 3 experiments have been done in this project. First is the feeder repeatability test on the research question of how does the design feeder mechanism can improve the accuracy. Second is to verify the reliability of the lateral swing design on the research question of how does this design can launch the shuttlecock by following the assist trajectory equation. And third is the launcher accuracy test, whether the launcher can improve the accuracy. So this is the prototype drawn by using the SolidWorks and all the values with the dimension of the machine in millimeters. And this is the real prototype fabricated. So let me show you the video for the demonstration of feeder mechanism. This video is recorded to test the accuracy of intersection between the racket and the shuttlecock. So from the first experiment, which is the repeatability test, we can get these 2 results. The figure shows the data point collected by using both new and mixed shuttlecock. So the shuttlecock is colored by the pen, and the feeder will drop the shuttlecock to the paper below the machine. So from the result, we can get the range, means, and standard deviation for both the mixed and new shuttlecocks. As we can see, the range and standard deviation for X and Y axis are different. In the table, the X axis shows a wider range and standard deviation than Y axis. However, Y axis is more important. Why does it happen? This is because from this figure we can see that the shuttlecock drop to the racket should be as near as possible. Therefore, the standard deviation should be as low as possible. While the x-axis, it doesn't matter as long as the range is within the diameter of the racket. So if the shuttlecock drops behind the reference line and intersect with the racket, it will be direct to the left. While if the shuttlecock drops in front of the reference line, it will be direct to the right, which is considered inaccurate because we want the shuttlecock to go straight. Next, this video shows the MATLAB simulations to test the model-free positioning. So from the simulation, the velocity is set to 10.2 for all the 3 trajectories, and the angles is 22.5, 45, and 67.5. So this figure shows the simulation curves for 3 different angles with the same speed. So from the simulation we can get this graph, and as you can see, as the angle increases, the y-axis, which is the height of the shuttlecock trajectory, increase. However, the distance travel x increased from 22.5 to 45, but when the angle exceeds 45, the shuttlecock will be decreased. I mean the distance travel will be decreased. So this is the video showing the experiment done by the lateral swing design. This video analysis is simulated by using a software called Tracker 4.84. It will track the trajectory of the shuttlecock during the operation. We can see, so the machine is set to a same speed and angles. However, the shuttlecock launched to different direction. Different location and different height. So from the video analysis, we can get this graph with 5 different shocks and the data showing here. So by comparing between the simulation from the MATLAB and the experimental result from the video analysis, we can calculate the accuracy in terms of error. So as we can see, the distance travel, the error percentage of distance travel is greater than the height. The error percentage is lower, which means higher accuracy. So the last one is the experiment of launcher accuracy test. So these two figures shows the result and the data point collected with the angles of 22.5 degree and 67.5 degree. However, for the 45 degree, there are no shuttlecock land on it. So this is as mentioned before, the shuttlecock is colored by the pen and landed on the piece of paper at a specific area. So the number of shots achieved by different angle setting can be get. As we can see, the accuracy for the angle setting of 22.5 degree is 20%, while the 67.5 degree achieve an accuracy of 60%. So why does it happen? These two figures shows the motion pattern of shuttlecock at different angles, these two angles. So for an angle setting of 22.5 degree, the landing position will affected by the structure of shuttlecock. This is with different types of structure, different structure of shuttlecock, the trajectory of the shot will be different. While for the angle setting of 67.5, the shuttlecock is pulled by gravitational force during free fall, thus more accurate shot can be achieved. However, it's still affected by the structure of shuttlecock, but not that great. It doesn't affect much by the structure of the shuttlecock. And as a conclusion, the linear model trajectory equation gives well description of the shuttlecock motion. Thus, by giving appropriate velocity angles, the distance traveled by the shuttlecock is said to be reliable. So this is the video demonstrate how the machine works for the training. Thank you. So these are the reference for this video, this slideshow, and these are the appendix, Gantt chart, the flow chart of the system. This is the time required for the intersection of racket and shuttlecock. This is the data sheet of the scooter motor used in the launching mechanism. This is the time calculation for the intersection between racket and shuttlecock.